Good morning. My name is Vishnuvardhan. I am from Electrical and Electronics Engineering, and my today's electric circuits TikTok topic is Kirchhoff law for nonlinear transfinite networks. Let's see. Kirchhoff law hold only sometimes in transfinite networks. For nonlinear network, there are presently just a few preliminary results regarding when they do hold. This work establishes more explicit and broader conditions for their validity in nonlinear transfinite networks. It also presents a fundamental theorem for the existence and uniqueness of the voltage current regime in such a network. This theorem is dual to the one current extent. Introduction. It is by now fairly well known that Kirchhoff's law need not hold in a linear infinite resistant network, nor need they hold in transfinite generalization of such network. However, certain sufficient conditions on the linear resistance can be stated that the satisfaction of those laws at particular nodes of infinite degree and around certain transfinite loops. The purpose of this paper is to devise such sufficient condition for Kirchhoff's law in nonlinear transfinite networks. The nonlinearity of the resistances complicates matters rather considerable and requires a substantially more sophisticated analysis. The required brevity of this paper presents an exposition of the required mathematics. However, what's needed is available elsewhere. See 1 or 2. Our notations and terminologies follows that used in these sources. The development of the sufficient conditions for the validity of Kirchhoff's law requires a new fundamental theorem for the voltage current regime in a nonlinear transfinite network. It has a dual form as compared to theorem 4.8, but in fact covers a different class of nonlinear network. The needed theorem is present in section 2. Section 3 presents the principal results of this paper. Nonlinear generalization of Kirchhoff's law for nodes of infinite degree and loops of transfinite length. The conditions for this to hold are rather complicated. Section 4 represents a simpler and more restricted but more comprehensible set of conditions for the validity of Kirchhoff's law. Fundamental theorem. Transfinite electrical networks can be ranked in according with the degree of transfiniteness. Those of the lowest rank, the zero networks, are simply the usual kind of infinite network. The networks of next higher rank, the one networks, are obtained by connecting zero networks together at their infinite extremes. Then we have the second network, two networks, which are connection of one network, and so on the higher rank. In this paper, we restrict the rank of the transfinite network and under consideration to an ordinal no larger than omega, the first transfinite ordinal. However, there does not appear to be any obstacle to extending our result to any countable or ordinal rank. We index the countability many branches in n by the natural numbers j equal to 1, 2, 3, so on. We assume throughout that every branch is a series connection of a pure voltage source in series with a nonlinear resistance Rj, which is a continuous, strictly increasing odd bijection of the real line R1 into R1. Gj is the inverse function for Rj and has the same properties. For f u belongs to R1, we set mj of f equal to integral of 0 to f rj into x dx and mj into u equal to integral of 0 to u gj of y dy. As for the voltage sources, we assume that the vector E equal to E1, comma E2, comma so on is a member of the modular sequence space LM. That space is a branch space with the norm. It is in fact a generalization of the classical space branch space. Under the conditions, we shall impose momentarily the dual of LM is LM, which is defined by replacing the MJ by the MJ in the above norms. LM is a generalization of LP where P inverse plus Q inverse equal to 1. We interpret each member of LM as a voltage vector in N and each member of LM as a current vector in N. Conditions 2.1. N denotes a nonlinear resistive V network, each of whose countable many branches consist of a series connection of a voltage source EJ and a nonlinear branch resistance RJ. There is no coupling between branches. The voltage source vector E equal to E1, E2 is a member of LM. Every branch conductance Gj equal to Rj inverse is a continuous, strictly increasing odd bijection of R1 onto R1. Condition 2.1. N donates a nonlinear resistive V network. Each of voltage many branches consist of a series connection of the voltage source Ej and a nonlinear Rj. There is no difference between the voltage. The source voltage vector equal to E1, E2, E3, and every branch of conductance Gj equal to Rj inverse is a continuous, strictly increasing odd bijection of R1 onto R1. Condition 2.2. There are a positive integer J0 and two numbers alpha and beta both greater than 1 such that for every j greater than or equal to J0, f of Rj of f is less than or equal to alpha of mj of f for 0 to f to aj, where aj is the unique position number for which mj of aj equal to 1 and u of gj of u is less than or equal to beta mj of u for 0 less than or equal to u less than or equal to dj, where dj is the unique pos- positive number for which mj of dj equal to 1. Under condition 2.1 and 2.2, Gj is a bijection of Lm onto Lm for any W equal to omega 1, W1, W2 belongs to Lm and any S equal to S1, comma S2, comma belong to Lm. We set W, comma S equal to bijection of W omega j Sj. It is a fact that the right-hand side covering absolutely. We now define L naught as the span of all basic currents in N as basic current being a transfinite generalization of a loop current. Finally, V star will denote the space of all W belongs to Lm such that W, comma S equal to 0. This equation is a generalized form of Teligand's equation. It requires the vector omega to be orthogonal to the current vector S. Also, V star is a closed linear subspace of Lm. Here is the needed fundamental theorem. It proves is much like that of theorem 4.8. Theorem 2.3. Under condition 2.1 and 2.2, there exists a unique voltage vector V belong to V star in N such that W, comma G of V plus E equal to 0 for all V belongs to V star. Kirchhoff law. Kirchhoff laws are consequence of theorem 2.3 when certain additional assumptions are placed on the branch resistance and conduction function. Consider first Kirchhoff's voltage law, which is also known as KVL. Definition of perceptibility. Let L be a loop of whatever rank and let L denotes a summation over the incidence J for the branches in L. L is called perceptible if for some positive numbers omega not depending on J. Integral of 0 to a rj of x dx is less than infinity. Note that every zero loop is always perceptible because it has only finitely many branches. Kirchhoff voltage law for a perceptible transfinite-oriented loop L asserts that summation of plus or minus Vj equal to 0, where the summation is over all branches in L and the plus sign is chosen when the orientation of the branch voltage drop Vj agree with the orientation of the loop L. To state Kirchhoff's current law for an node of infinite degree, we need another definition. Definition of restraint. Let n denote a zero node which is ordinary. That is, n is not shortened to any node of higher rank. Let donates the summation n donates a summation over the incidence j of the branches in the incident to n. N is called restraining if for some positive number n not depending on j. If n is a finite ordinary zero node, it is automatically restraining because the summation has infinitely many loops. Kirchhoff current law for for a restraining ordinary node is node n of infinite degree asserts that summation of n plus or minus ij equal to 0, where the summation is all over branches incident to n and the plus sign is chosen if the branch current ij is oriented towards n. This law holds under the hypothesis of theorem 3.1. Assume condition 2.1 and 2.2 and let the voltage current reside in n be that dictated by theorem 2.3. Then Kirchhoff voltage law holds for every perceptible loop L and Kirchhoff current law holds at every ordinary restraining node N. More understandable conditions. Condition 2.2 are rather absurd with regard to the properties that the resistance and conductance function must have. Since modular sequence space generalize the classical LP space, simpler conditions that reflect the structure of the LP space are to be available. This is true. Accordingly, we state in this section as a stronger but more understandable replacement for condition 2.2. In the following, P and Q denote real number both greater than n such that P inverse plus Q inverse equal to 1. Also, AJ and DJ are defined as, as in condition 2. Condition 4.4. There is a positive integer JO such that for all J greater than JO and for all O greater than O 0 less than or equal to F less than or equal to max F by Rj whole power P minus 1 is less than or equal to Rj of F less than or equal to Pj of F power P minus 1, where Rj and Pj are positive numbers such that Rj power P minus 1 of Pj is a constant that does not vary with J. The bonds imply that Rj power P minus 1 of Pj is greater than or equal to 1. They are illustrated in figure 1. Lemma 4.2 assume that the condition 2.1 hold when condition 4.1 implies condition 2.2. By virtue of lemma 4.2, we have theorem 4.3 with conditions 2.2 replaced by conditions 4.1. Therefore, 2.3 continues to hold and Kirchhoff law also holds as stated in theorem 3.1. Another simplification also arises from inequalities. They yield more constant condition for the perceptibility of a loop L or for the restraint of an ordinary O node. And fourth, we do not require to hold for all but possibly finitely many of the branches of n. Instead, we revert to condition 2.2 when invoking theorem 2.3. The bonds are now only imposed for the branches in a given loop or incident to a given node. Theorem 4.4. Given a transfinite loop L, let J be the index set of all but possibly finite many of the branches in D. Let omega be some positive number that does not depend on J belongs to J. If the right hand inequality of 6 holes for J belongs to J and 0 is less than or equal to F less than or equal to lemma, then summation of j belongs to j, pj is less than infinity is a sufficient condition for L to be perfectible. If the left hand inequality of 6 holes for j belongs to j and 0 is less than or equal to f less than or equal to lemma, then sigma j belongs to j or j power 1 minus p is less than infinite. Infinite is a necessary condition for L to be percentable. If C equal to Rj power p minus 1 pj is a constant independent of j belongs to j, and if both inequalities of 6 wholes for j belongs to j and 0 is less than or equal to f less than or equal to lemma, then summation of j belongs to j, pj is less than infinite is necessary and sufficient for the percentable of L. Since g of j is the inverse of r of j, 6 can be written as u by pj power q minus 1 is less than or equal to gj of u less than or equal to rj of u power q minus 1. Theorem 4.5. Given an ordinary infinite zero node n, let n be the index set of all possible finite many of the branches incident to it. Let n be some positive number that does not depend upon j belongs to n. If the right hand inequality of 7 holes for j belongs to n and 0 is less than or equal to u less than or equal to n, then summation of j belongs to n, gamma of j is less than infinite is a sufficient condition for n to be restraining. If left hand inequality in 7 holes for j belongs to n and 0 is less than or equal to u less than or equal to n, then summation j belongs to n, p of j power 1 minus q is less than infinite is a necessary condition for n to be restraining. If p of j power q minus 1 into r of j is a constant independent of j belongs to n, and if both inequalities hold for j belongs to n and 0 is less than or equal to u less than or equal to n, then summation of j belongs to n, gamma j is less than infinite is necessary and sufficient for the extent of n. Thank you.